mechanical engineering, and I'm going to talk to you about making things and the technologies that make modern design and manufacturing possible. Can you see this? Because if not, try and get yourself in some place that you can, because there's a lot of slideshow to follow. I'd hoped to use the overhead projector, but as you may have found out, that one is flaky, and our chemical engineering colleagues haven't got it repaired yet. Okay, I think people have been telling you what engineering is. Let me give you my view of what engineering is. It's this. It's making what you need from what you can get. And the essence of engineering, as I understand it, really is changing the world. I'm less interested in understanding how the world works than in making it better. And that's how you do it. Well, I'm going to start this with a few cartoons which are going to summarize a few thousand years of history. And this is basically design and manufacturing history. Now, if you can't hear me, please let me know. And if you can't see through me, let me know that too. I'll try and stand to the side. Let's start here. And the idea is that in all product systems, you have some sort of customer, and you have something that's to be done or accomplished, a chair, something to sit on, or a table. You have someone who's going to do it, build it. Then you have a product, which goes back to the customer. Now, sometimes these are the same person, but the components here, some sort of functional goals, and then something that results are constant throughout this system. Now, that's the way things work simply, and that's the way you may build some very simple products yourself. But the big change that came in next was the notion of a design. Design is a thing. So you had a customer and some needs, and the artisan scratched his head about these and produced a design which was a prediction, if you like, or a model or some specification of what the product would be like. And the customer said either yes or no, or change it here and there. And they went around this loop until you finally had a go-ahead from the customer. Then the product got made. Now, see, this is something all in itself, a design. Up here, the notion of design is existential. That means it's floating around in your head somewhere. And it's only when you can make some kind of physical manifestation of it, we'll talk about that soon, that you can communicate it to other people effectively, or communicate it to computers which drive machine tools. Well, that's a basic system. Now, this got elaborated in time. And the next version of this had some specialization appearing. So you had designers now, artisan designers and designs, but you had builders. And they worked from the design and they produced the product. That system still goes on, and this is called an artisan-based system for reasons you'll see soon. And this was all, this sort of system ran beginning thousands of years ago, and it ran right up through the Middle Ages. And one of the characteristics of old times was that things were made in very small quantities, like 1 or 2 or 3. And if you wanted to make 25 arrows because you were going to war with a bow and arrow, that was a big lot of stuff to make. And this system worked well enough for small quantities. Now, when the quantities got bigger, so if you want 500 muskets for a 17th century army, for example, you had more customers and one design, and now you had artisan builders. Now problems started to arise. And these products, muskets were the first example which caught the headlines at the time, would break down in the field. And the users wanted to repair their muskets in the field. And if they had a broken lock, for example, or a trigger mechanism, they wanted to just fix the trigger mechanism. And they couldn't do that. there was no notion whatsoever of interchangeable parts or replacement parts. So if you needed to repair a musket, you better have a blacksmith handy who can make you a new part or fix the old part. But this is the way products were made, and this is when quantities began to increase. Now this system persisted into the early 1800s. And along about, or before 1800 and into the 1800s, mechanization occurred in a big way. And the system was really run on animal power and human power before then. Water power came in, and then steam engines came in. And this enabled you to make stuff faster and more repeatably, and you could make a lot more of it. And the question then of replacement parts and product standardization became acute, because you couldn't extend this system to make thousands or tens of thousands or millions of a thing. So throughout the 1800s, the whole system of interchangeable parts came in. And this is a remarkable system. It's the way production runs today. And here's the idea. I have electrostatics. You now have builders who are specialist builders, and this builder, who might today be a machine tool, automatically driven, only knows how to do one thing. Now tomorrow it might build a different part, but today it's always building this kind of widget. And this particular component goes in all these products, and this one builds a different kind of component, and so on down the line. They all go together in these products, they all fit together, and the product works. Now, that's a remarkable system, and to make that go takes quite a lot of high technology and quite a lot of management skill. And that's in part what we want to talk about today, what makes this thing go. Notice that you benefit greatly because this allows you to replace parts. And if something in a car, if you own a car, breaks, you can go to Napa or similar and simply buy a new water pump or a fan belt or whatever it is you need, and it will fit. Good. Well, if you think back on that, you say, what are the issues here? What are the primary drivers of this system? And there are really three. There's the notion of design. Now, design as a word can be taken in two ways. It's a noun and it's also a verb. So the noun means the design. It could be a model, it could be a computer specification, but it specifies a product or a component. The process is how you get the design, that is to design or designing. And that is, well, you'll spend 4 years learning about that, and you'll know a little bit about it then. It's hard, it's fascinating. Then there's fabrication. You have to make parts, you have to put them together, and there's enormous variety here, as you'll see. Then there's this more subtle business, which is the management of variability. The ability to do this, to manage variations, is what allows you to have interchangeable parts and allows you to make things in large quantity. And you might say, well, where's the variability come from? It's everywhere. And nothing in the world of engineering is precise. And every machine tool has finite precision and will not make you precise parts. They will make good approximations to precise parts, but not perfect parts. People, operators, machines, they all have ranges of error. Materials vary, their strength varies around nominals. So you have to deal with all this variability. Now, there are two strategies. We've talked about the artisan strategy, which is simply custom fitting. Make a part, start to make the second one, and just keep filing until it fits with the first one. And do the third one the same way. Industrial practice, well, this is interchangeability and dispersion of effort, as the diagram showed. Let's look at these a little bit, and let's start with design. Okay, I've said designs are existential, meaning they start in your head. And the question now is, how are they represented, put into something tangible you can communicate? Well, what are the options? If you have an idea for some simple product in your head, and you want to describe it to me, or to a technician who's going to build it for you, what would you do? Anybody?
Draw a picture.
Yeah. You could draw a picture as long as there's some agreed conventions for what pictures mean and how you look at them. That's one. That's modern. If you could put yourself back a few thousand years, what would you do? Well, you might make a sketch in the sand. You might make some kind of model. Or you might have some idea of how you might make it, and you would tell the other person how to make it. So you would describe the part by how to make it. So these are the three ways that you have for dealing with this question. There are models, and architects still love models. You'll find lots of architectural modeling supplies in the campus store. Naval architects made models, and right up into the early 2000s, almost all warships were really defined by physical models. Models have problems. You have to scale them, you see, and that's subject to inaccuracy. And you have to specify what the variability allowances are when they have many parts. That's very hard to do on a model. Models wear out. If they're wood, they're subject to humidity, and so on and so forth. Procedural specifications. So don't describe the thing, describe how to do it, how to make it. And get yourself a piece of wood and saw it off here, and then do some planing there, and then drill a hole. That's okay, as long as whoever is to make it can get the same sort of piece of wood and has the same set of tools to do the same sort of machining you have. But if you were to send this prescription to an Oriental country where the tools are different, you don't know what you would get. So we're come down to symbolic systems which really rule the roost now. And graphics, two-dimensional graphics, drawings, were really the entire story for probably 500 years. And it was only in the past 30 years that mathematical models and modern CAD, computer-aided design, have become reliable enough to use. And today they're really quite good. Well, let's look at some of the history, because I think it's interesting. So this is about initially the history of graphics. Here's a little timeline. Yeah, that's worth a quick look at how things evolved. Modern graphics started really with René Descartes, who invented algebraic geometry. His treatise was 1637. Descartes was a philosopher who you may know a little bit about. He was an astonishing giant in history. Then go ahead about 170 years, and you come up to descriptive geometry, which is the kind of geometry used in engineering drawings. You may have learned some of this in high school. And this was devised, the conventions were set by Gaspard Monge, who was a French military engineer. And as soon as he produced his treatise on descriptive geometry, Napoleon immediately classified it, called it the military secret, and because it was very useful in building fortifications. And so it remained for almost a decade. Well, in the later 1800s, you began to have dimension drawings, then standards. 1950, computers and numerically controlled machine tools. These evolved basically separately, to the detriment of machine tools, unfortunately. They just began to converge perhaps 20 years ago. Computer-aided drafting, early CAD, modern CAD began to appear about 1980. Okay, what are a few tangible examples of this? First example I've been able to find. This is about 1300. And this is the specification for what? What do you think that is? Well,
Water wheel?
it's a water wheel. The water wheel is doing something. This is a gear. And what's the gear doing? Well, look, if you look up top, look up here, what's the...
A mill.
It's a mill, yeah, some sort of grain mill. Okay, well, that was pretty crude, but you were able to decode it. Now, people got more skilled and began to have rules. This is about 1400, just before cannons became widespread. This is a war machine. I think it's called a trebuchet. It throws rocks. And notice the graphic conventions. This is drawn in a form of perspective, and it's pretty good. You could duplicate it, not to exact dimensions, but in general structure, really from that drawing. Okay, well, people got more skilled, and the conventions got more elaborate. And let's see. Okay. Now this is 1795, and it's an early steam locomotive. But this really is the definition of the locomotive. There were some individual part drawings. I'll show you one soon. But there were no dimensions on this drawing, and you use the following. If you look, you can't see it probably, but this is a scale, and it's denoted in inches up here, and these are feet. But this wasn't a very big gadget, see. But that was the only way you had to get sizes and stuff off this drawing, but that defined the steam engine, or the locomotive. Now, well, things progress through isometric conventions. I won't bother with those. All right, let's jump into the modern age, or almost. And you have things like this. Now, I'm going to assume that some of you, maybe many of you, know just what this means and could reproduce this, or in other words, could make perspective sketches according to the rules of perspective drawing. CAD systems will do it for you now, but it's a good thing to know how to make these sketches and what the rules of perspective are. Well, this is sort of engineering graphics just before the computer appeared. It's what I learned when I was a student engineer. And you should know, or you'll learn if you don't know now, about the layout conventions for drawings, and put them out right. So, and you have such things as a top view looks down, and a front view looks that way, and a right profile view looks that way. And you can remember this in terms of unfolding boxes, which I presume a few of you, maybe many of you know about. If not, again, when you learn some CAD, you will learn some of this stuff. Well, okay, computers arrived. And the first attempts to computerize engineering specification were not very clever. They simply sought to computerize drafting. So you had commands like define a point, and define another point, and put either a line through them, or put perhaps an arc through them with a defined center. So you could make lines and curves. That's what you could do. Then you could hook them together, and how you hooked them together was up to you. Now, if you wanted to define solids, you had better hook them together right. And for 15 or 20 years, no one quite knew the rules. So you had funny situations appearing. Here's one. Now, this is an isometric drawing of a solid with just the edges are shown, and there's no hidden edge suppression here. And just figure out what the solid is in your mind. You got it? Well, now, what I see right now is a solid in which I can push my fingers through the slot here. Everybody see that? Well, you might, some of you might think you could push your fingers through the slot that way. And still others would say, I'm going to push a finger down there. Like that one. Well, they're all right. You see, this is not an unambiguous representation. So there are three solids represented by these things. Which one do you mean? Well, that won't tell you. So there were things like that which wasted a lot of money. And you had some even weirder ones. It was very easy in the wireframe systems to define that. Now, these early wireframe systems had in them routines for calculating mass properties. Moments of inertia, products of inertia, volume, things like that. And if you turn loose one of these algorithms on that, what do you think you would get? Well, if you were lucky, you would get a crash, or you would get a rude message. Because you see, that's not a physical object. It's a non-oriented solid. If you don't see this, just try and walk yourself around it. Okay. The worst thing you could get, and what did happen sometimes, is that you would get a credible answer. And you wouldn't know that this was not a legitimate solid, and you might try to machine it or something. And then you would have a serious machine tool failure in your shop. So, again, a lot of money down the tube. Modern CAD systems got this fixed about 1980, and now they're quite reliable. Well, that's enough on the mechanics of design representation. Learn to use your CAD run and love it. I'll talk just briefly about the process of design. Mechanical design is different than other kinds of design, and it's hard. Now, the main reason is that mechanical design uses a lot of function sharing. One of the principles in most design is modularity. So if you're an electrical engineer and someone tells you to build a widget to do this and that, you will go to your box of standard parts of shift registers and gates and ring counters and things like that and put them together to make your widget. It's just really an assembly operation. If you're a chemical engineer, you'll do probably similar with basic chemical unit processes. In mechanical engineering, you can design this way. And so each part you put in your product does just one thing. But you will not get good products this way. They will have too many parts, and they will be heavy, and they will be expensive. Let me show you an example. I can find my example. Yes. All right. This is a modular design. And what does it do? Well, it's not so hard to deduce that. These look like cutters of some sort. And this thing, I think, obviously goes down. This is a guide. This is a spring. The only job of the spring is to exert upward force against downward pressure. This is a lever and a cam which push this thing down. So you have some kind of a cutting machine here. Okay? Now, if you want to design that right and design it for a market, have a nice reliable product, you make this. Okay? What's going on here? Well, these components, of which there are four, with two of them welded together at the end, do a number of things. They operate as springs, they operate as cutters, they operate as levers, and so on and so forth. And this is true through almost all mechanical design. Think of the door of a car. And just sometime when you are sitting around musing, write down mentally or on paper the various things that the door of a car does. And you'll have quite a long list. It adds structural strength, it keeps the rain out, it adds aesthetics, and so on. Those are the easy ones. Let me give you one you probably would not think of. It's a link in the electrical ground chain of the car. See, and there are lots of things like that. So it's function sharing which makes mechanical design so challenging. Okay, let's go back to our shopping list. And we were, you see, talked about design. Let's talk a little bit about fabrication and making parts. Well, mechanical engineering is blessed with an enormous number of processes to make things. And there's a little taxonomy here. So these are families of processes to make parts. And starting up here, you have some changes which are mass change processes. And machining goes in here. You see it, you machine stuff away and you take away mass apart. And you have additive processes too. Phase change processes. This is when you start with a liquid, you put it in a mold and it solidifies and becomes a solid. You change the phase of the material. Deformation. Lots of these. You bend sheet metal, you force things through dies, you bang on things with hammers, as in piston rods to strengthen them, etc. There are consolidation processes. You put together metal powders or you make fiberglass-like compositions and so on. Then there are structure changes, and these really affect the internal structure of the material. Surface hardness, directional grain properties, so the material becomes anisotropic, and so forth. Now, we can say more than that. If you look up here on the mass change processes, well, you have the subtractive processes. There's conventional machining, and there's chemical machining and electric machining. All of these remove material. In conventional, you have turning, milling, grinding, and so on. Under additive processes, you have plating, the layered freeform ones that are really coming into play now, like plasma sprays and stereolithography, and there are more of those. Now, all of these down here have the requirement that they require custom tooling. And so it's unusual to use these if you're only going to make one of a kind or maybe two of a kind. Not always true. There are some products of which you make only one, for which you really must cast it. And that's true for some others. But you have an overhead cost of tooling, dies, molds, and stuff like that, which restricts some of the use of these. So these are popular and important ones. Now, let's look just a little bit at one, and we start with talk a little bit about phase change processes. Then we'll go back and talk a bit about machining. Here on one form is a taxonomy of phase change, now our casting processes, molding. First, what is it? Well, you make a distinctive solid shape by cooling a liquid in a mold that is the spatial complement of what you want to make, the shape to be produced. So, you need a pattern, that's the model of what you're trying to make. You need the mold, which you make from the pattern, which you put in the material, the liquid material. Then you need the material itself, and then you have some characteristics. Now, there are four families of processes which work this way, and here they are. There is investment casting, sand casting, die casting, and injection molding. These two are quite similar, but this one is for metal, and this one is for plastics. Sand casting is used, well, to a great variety of shapes. Almost all of the engine blocks in cars worldwide are made by sand casting. Almost all of the brake drums for drum brakes are made by sand casting, and so on and so forth. Investment casting is used very lightly. Just look at a couple of these quickly. For example, investment casting. It's expensive to do. It's used for small quantities of small, precise parts. Jewelry, turbine blades in gas turbines and similar. They have exotic materials. They have complicated shapes. You can use it for any metal. Here's how it works. Your pattern is sacrificial. It means you're going to destroy it. Typically made of wax. Your mold is sacrificial too. And you take your wax pattern and you embed it in a ceramic slurry. And then you cure or bake the slurry. And so you have a very hard ceramic mold. You have to get the pattern out. How do you do that? Well, you just heat the mold. And wax melts and it runs out. But then, of course, you've lost your pattern. And then once you have your mold, you pour in your metal. Then you have to get your cast part out of the mold. How do you do that? You break the mold. And so the mold is sacrificial too. And finally, you have this very precise part. So for every turbine blade in a gas turbine, or steam turbine, you start with a new pattern and you make a new mold and so on and so forth. That's why it's expensive. But it's precise and you can use it for very high temperature metals and so on. Sand casting. We'll do this very quickly. Reusable patterns. Typically they're made of wood with several parts in the wooden pattern. The mold is sacrificial because it's clay-infused sand. And you have boxes called core boxes. You put your wooden pattern in the box, put sand around it, you tamp the sand with a power tamper, and you bake it to harden the clay. Then you pour in it typically steel, iron, things like that. And then to get out your part, you simply destroy the sand mold. Do it again using the same pattern. Well, the other two use high precision metal dies. The dies are very expensive. This one, die casting, really is only suitable for low temperature alloys of zinc, copper, aluminum, tin, and so on. And the injection molding is for polymers, of which there's a great variety. But the machinery is similar, but works at different speeds and different temperature ranges. Very expensive dies. You don't want to use these to make 2 or 3 of something. You want to start with making 5 or 10,000. If you were taking apart power tools in the lab, almost certainly quite a number of the components were injection molded. And you ought to be able to see this with little circles which were the pins that push the thing out of the mold. All right, machining. What goes on in machining? Here's what the basic physics models are based on. You have a cutter, you force it into material. This is feed. You're pushing it here either manually or in a machine tool, a cutter, and you make a chip. So what happens here is you create a shear zone. The material first deforms plastically, then it deforms elastically, and finally you push it way past its yield point and it breaks, and the chip breaks off. About 60% of the energy you use goes into this process of actually tearing away the chip. And the rest of the energy goes into friction. A lot of friction here and friction on the tool face. And now this very basic material processing step is embedded in lots of different tools. And the most common thing, most machining you do in engineering is to make holes. Lots and lots of holes. And here are some of the tools you use to make holes. Twist drill, everybody knows about. Reamer makes precise holes. Twist drills make lousy holes. They're not very round and they're not very straight. If you want a nice round straight hole, you either make it after you've twist drilled it, or you have to bore it with a boring bar. Then you have the specialized holes, taps, and this is a counter bore which makes shoulders on things. Well, those only make round holes. If you want to do other kinds of things, you need different kinds of cutters. And next year, when you get in your sophomore lab, you use this stuff. You have end mills, plane cutters, side mills, face mills. key cutters, slot cutters, and ball mills, and so on, a big variety. And you can use these to make a big variety of shapes. Now, this is all sort of the superficialities. What can you make with a machine tool? Well, there are certain characteristic shapes which are governed by the motion that the machine tool can execute. And I could show you some pictures of machine tools, but I don't think I will. You go look at them in the lab. Here is one of the crucial characterizations. What's the geometry you can produce? Well, with drilling, boring, and reaming, all you can make is straight cylindrical holes. With face milling, you can make plane surfaces. With profile milling, you can make ruled surfaces. These are surfaces which are curved, but they're always normal to a single plane. With end milling, you can do ruled surface and approximations to general surfaces. Turning makes, on a lathe, rotationally symmetric surfaces. Everything you make on a machine tool, every complicated shape, is made up of approximations using these pieces of surfaces, pieces of plane, pieces of cylindrical surface, and similar. Well, that's a gross shape. And the critical point now is how accurate is this stuff. As I've said, twist drills are really very imprecise cutters, which they are. So you have a whole complementary set of data, of which this is a tiny subset. Don't try and read it, I'll tell you what this is about. These are processes, drilling up here, down here, honing and lapping and grinding. This is, take it as precision, it's called tolerance, but you have 2.5 orders of magnitude of accuracy, if you like, or fineness of finish. And this is a general scale of the process. So, big range of differences in precision. And depending on what you're trying to make, you must choose your process with care. If you're building engines in which the pistons must fit well into the cylinders, well, you better do some honing and lapping and maybe some grinding. Don't try and do it all on a lathe. Okay, what do we do now? How are we doing? Well, we're almost getting out of time. Let's go on to our final topic, which is management of variability. We talked about the artisan strategy a little bit, and there's not much to say. It's custom fitting. Now, let's look at this industrial practice of interchangeability and see a little bit of how this arose. And let's see how we start this. Remember the locomotive we had up a while ago? This is one of the components in the locomotive. This is a beautiful longhand script. I doubt if you can read it. It says this is a regulating throttle cock. What that means is it's the valve which controls the steam flow to the cylinder. And the date on it is 1804, and it tells you the scale is half size. That is the complete definition of the part. And the people in the workshop are supposed to make this thing from this definition, put it in the engine, and the engine is supposed to run. Well, how do they do that? You see, there aren't any numbers on that. All it does tell you is half size. And this was a drawing made in ink on starched linen, which was the medium for archival drawings at the time. Well, the basic limitation, one of the limitations around 1800, was that you could not measure. And in the shop, the best you could do was perhaps 1/10 of an inch. There were no fine steel scales with engraved markings on them. There were no micrometers and things like that. The basic working tool was a proportional divider. And if you can't measure, then you work proportionally. So every shop person had a whole set of these proportional dividers. And they had various ratios. This is a 2-to-1 ratio. So to deal with that throttle cock, you would go to the drawing and you would scale it up on this end, and you would lock it with your thumb screw here take it out into the shop, and make the part until it fit within that size. And that's how you made things from scaling drawings. Well, this was the way things were up until the middle of the 1800s. Yet before that time, there were very strong efforts to have interchangeable parts. And the military, especially the American Army, put a lot of money for the time into people like Eli Whitney, who promised to make muskets and revolvers with interchangeable parts. This was about 1825 and 1830. Well, they managed to do it, sort of. And how did they do it? Well, with gauges. And gauges are like a fixed form of a proportional divider. It's not a way of measuring, but it's a way of controlling shape. Now, here are two different sets of gauges. Look at the bottom ones first. These are the inspection gauges for the 1841 U.S. model Springfield rifle out of Springfield Armory in Connecticut. Springfield, Massachusetts. These were built in Connecticut. All of this technology came out of Providence, Rhode Island, and one or two sites in Connecticut. It all came into being over about 30 years in the 1800s. Anyway, here you have a set of very fine, typically brass gauges with lots of little slots and things like that. Various parts of the rifle had to fit in some slots and not fit in other slots. These were go, no-go gauges. And the people making the parts had access to these things, and that was how they made them to sizes. And the people who devised the gauges did so to make sure the rifles would assemble interchangeably. The gauge makers were extremely clever people, and we still don't know what rules they used. Well, these were gauges on the civil side for making wooden clocks. These are marking gauges as well as measuring gauges. You'll see here little pinpoints to mark wood in a lathe, which would turn this part, which was one of the spindles in the wooden clock. That was the technology in the 1800s, and as modern forms of these are still used. They're used quite widely in the automotive industry. Big major advance, about 1855. Vernier calipers like this and micrometers became affordable. And Brown and Sharp in Providence brought forth this one, which cost you $4 at that time, and with a Morocco leather case, $4.50. This was the gauge of 1867, a little after the first one. The vernier caliper came slightly earlier, 5 or 10 years, in production quantities. The whole notion of the vernier scale came out of France in Napoleon's time. Once these got on the shop floor, and $4 was a price that craftsmen could afford, things began to change quickly. And the first change was that designers began to put dimensions on their drawings. And after about 30 years of putting dimensions on, they began to put tolerances on, because there was disagreement over what dimension was accurate, made against drawings. Now, this typical drawing of 1900, and this is what I learned to make when I was a student. So you see a part defined by orthographic views. You see things like 1 plus and minus 0.01, 2.5 plus and minus 0.01, etc. Here's 1 plus and minus 0.005. And these gave you ranges of allowable variations of the dimensions. And this is what industry ran on from the late 1800s up through the Second World War. Now, there's a problem with these dimensions. They're ambiguous. And this came to the fore in the Second World War, and it became apparent because the Second World War was the first time that widespread outsourcing was used. Lots of, let us say, airplanes or tanks were to be made far more than you could make in one factory. So you had to produce them in multiple factories, and they were supposed to be the same and use the same sets of parts. But to do that, you had to have unambiguous specifications, and these are not unambiguous. I could show you why. Well, I guess I will. Okay, well, here's a very simple drawing. Length and height, plus and minus 1 in each dimension. If you produce this part, which is 5.9 by 305, you could say that's okay. Now if you produce this part, it's a little bit unclear, because this doesn't tell you what the angles are supposed to be. And they clearly cannot be exactly 90 degrees. How much off can they be? It doesn't say. This is tougher. If you produce a part of imperfect form, what do you do with that? And everything you make has imperfect form. There's no such thing as a perfect plane or a perfect hole. You have to deal with form. And, well, the kinds of ambiguities you have and the attempts to deal with them are shown there, but suffice it to say there is no way to fix that limit tolerancing drawing you just saw without changing basically the way you approach variation control. What's happened since then is that we've gone to geometric tolerancing, which is a different sort of a system. I'll show you an example of it. This is a geometrically toleranced part, and it has lots of symbols on many of you may have never seen. This is a position symbol, and this is a parallelism symbol, this is a datum designation, this is a datum target, and so on and so forth. And these have very, very precise spatial meanings. And they clear up almost all of the ambiguities of drawings. But they take a lot of learning. It's tough to teach this in industry. It's difficult to teach it to university students. And the old system of these plus and minus tolerances on dimensions are still used in low precision industries. For example, in building construction, they're okay. You will probably be able to get by on those in most perhaps all of your sophomore projects. When you get into senior projects and start building race cars and things like that, you're going to be driven to this. And this is happening now in the Sibley School. Well, okay, I'm almost done. Now I had in the process of devising for you a homework problem. I ran out of time, but I think Professor Ruina will probably say, press on and do it. Let me tell you what it is. You may see this again. Nice problem. This is a disc brake. And this is the frame of the disc brake. This is the actuator, which is either pneumatic or hydraulic. It presses this way. This is the rotor wheel. And these are the pads. So when you push the pedal, the actuator moves this way and pushes the pressure pads against the rotor. Okay. Now, there are these various components here. Shut this door. These various components have dimensions, and the variability in these dimensions has to be controlled well enough so that you can be sure this gap is never negative. A negative gap means there is no clearance here whatsoever. And you won't be able to put the brake together unless you have some clearance. And the brake won't operate right unless there's a little gap there. But you can't have the gap too big because you'll run out of range of the actuator. And so there are limits on how much variability you can accommodate. Well, here's the symbols, here are some numbers, and tell me what the max and min of the gap are. Right? And you'll find it's, if you're clever at this sort of stuff, it's a 10 or 15 minute exercise. If it takes you longer, it might take you 30 minutes. So it's not a heavyweight problem. It's rather a fun problem. And if I do write it up and you do get asked to do it, I'll put in a couple of notes on how you approach the problem. All right, let's finish up. Strategies for coping with variability. Well, the traditional one is the artisan strategy. Still works if you only want to make one or two of a thing. Modern industry, interchangeability. It works through process-independent part and assembly tolerances. And it works through control of manufacturing processes to meet these tolerances. That's a crucial step. Now, we've run on this system for about 150 years. Are there new options? Is there some sort of post-industrial system? And is a third option emerging? Well, it's an interesting question. Are we desperate for an alternative to this? No. We're pretty good at doing this. And it works and it gives good products. And you can go to Napa and buy parts for your car and all that stuff. What might be the advantages of, so what are you looking for in an alternative? That's unclear too. Where do you look for models? Well, nowadays you might look to biology, and let me just leave you with the following observation, that your bodies are made up of parts, and their parts are assembled together to make a mechanism, and all the people in this room have about the same number of parts, and the parts look sort of the same. But they differ in detail. Now, these parts were not all made individually in different factories spread around the world. So they were all made in one place, and they were all assembled before they were fully made. And so the parts were evolving as the assembly varied compliantly to contain them. And so your parts all kept hooked together as you grew up into what you are now. Find the industrial analog. Well, that's enough for today. Thank you.